All right, so this is an example problem for Learning Objective 2 in our chapter on gravitation. I will tell you right off that I ask way more questions on this example than you should expect on an assessment, but I wanted to just give you some variety here in terms of the types of things you might see. Okay, so here's the scenario. We have a satellite orbiting Mars in a circular orbit. It's going to start with an orbit at an altitude of 1,000 kilometers, and then it's going to decrease its altitude to 500 kilometers. So there'll be sort of two different places that it's going to be in terms of its distance from Mars, and we're going to answer questions in both of those distances. If we're sort of visualizing this, if here's Mars, and here's where the satellite is. That's a terrible circle, but when I'm talking about the altitude, I'm talking about the distance from the surface of the planet. And so 1,000 kilometers and 500 kilometers are not our values for R, but I'm calling them values for H. And our R is going to be the radius of Mars plus that H. So our initial would be the radius of Mars, which is 3.39 times 10 to the 6 meters. And then 1,000 kilometers would be 1 times 10 to the 6 meters, because a kilometer is 1 times 10 to the third meters is 1 kilometer. And so that's how I got that value. So our first radius that we're going to be working with is going to be 4.39 times 10 to the 6 meters. Okay. So in part A, we're asked the speed of the satellite in this orbit. Because we're told it's a circular orbit, I'm just going to use this relationship, which I find is going to be a lot easier to work with, where we talk about the satellite being in a circular orbit, so it's going to be experiencing centripetal acceleration, and that acceleration is due to the force of gravity between Mars and the satellite. This is going to give me an expression for v squared that pretty quickly. So I'll write it as big G, the mass of Mars, over the radius. So I can input my values for big G for the mass of Mars, which you've been given. And the radius, which we just found. This gives me v squared. If I take the square root to get my velocity, I get 32.45, and this will be meters per second. Okay. In the second question, I asked, how long does it take to complete one orbit? Just thought that would be an interesting question. Of course, I'm asking for the period. I know you have an expression for period on your equation sheet, but to be honest, to me, it's going to be a lot easier to just solve this using the idea that rate times time equals distance. The distance the satellite's going to travel is going to be the circumference of the circular orbit, which would be 2 pi r, and then we divide by the speed, which we just found. That's going to be way easier than that expression you see on your equation sheet. And this is going to give me 8.5 times 10 to the third. This is going to be in seconds because of the units of my velocity. That's a big number, so I first tried to divide it by how many seconds would be in 1 hour, which would be 3,600 seconds. And that got me down to a reasonable number, so I'm going to stick with it, of 2.36 hours. I want to also just offer this disclaimer. I kind of made up this problem. I don't really know if these are reasonable orbits for a satellite, but I knew what I wanted to do with the problem, so I just made up these values. Okay, now we're going to look at another part of this question. We're going to say if the satellite moves closer to the surface of Mars and is in an orbit of altitude of 500 kilometers, what will the new speed of the satellite be? So this is a new radius. I'm going to call this radius final. And I did already call the first one radius initial. So I'm going to take the radius of Mars plus this new h. So the radius was 3.39 times 10 to the 6. And 500 kilometers is 5 times 10 to the 5th meters. And so my new radius is 3.89 times 10 to the 6 meters. In part C, I said to assume that no energy was lost or added to the system. Basically, I wanted you to be able to use the conservation of energy. So you look at the initial kinetic and potential energy and set it equal to the final kinetic and potential energy. So what we're saying is that when it was at an orbit of 1,000 kilometers, that was our initial location, and our 500 kilometer altitude orbit is going to be our final location. So we have 1/2 the mass of the satellite times its initial velocity squared, which this is going to be v initial. And then minus g, the mass of the satellite, the mass of Mars, over r initial. Right here's our r initial. And then 1/2 the mass of the satellite, velocity final squared, minus g, mass of the satellite, mass of Mars, over r final. So this is using conservation of energy to solve this problem. I'm looking for v final. And this is definitely, so in this chapter, we have a lot of really big numbers. And I think sometimes I've seen that it looks like people are having trouble inputting things correctly into their calculator because of the big numbers. I think that there's a lot to be gained by simplifying this expression a lot before I plug in my numbers. You know that that's my general rule. I stick by it. So the first thing I'm going to do to simplify this expression is I got rid of the mass of the satellite all the way through because it's in every term. And then I multiplied the whole thing by 2 to get rid of the half in front of the velocity terms. And so where I'm going to be right now is I would have v initial squared minus 2 big G, the mass of Mars, over r initial equals v final squared minus 2g mass of Mars r final. And I'm going to have to go on to another slide, because I'm running out of room. The last question was, the satellite will need to accelerate to escape from the gravitational pull of Mars and return to Earth. What's the escape velocity from Mars when it is in an orbit at an altitude of 500 kilometers? That slide is just blank, so I'm going to just rewrite where we had started. I had v initial squared minus 2g mass of Mars over r initial equals v final squared minus 2g mass of Mars r initial. So I want to solve for v final. I'm going to try to get v final squared all by itself. And so what I did is I took these two terms and I put them together by factoring out the g and the mass of the Mars and the 2. And then it's just times 1 over the initial radius minus 1 over the final radius. I'm just going to put in the numbers to just make sure we all know what we're putting in here. And then just put in some intermediate values. My numbers seem reasonable, so I think that I did everything right. If you find that there might be a calculation error, let me know. So I find that the velocity squared is equal to this number, which gives me a final velocity when I take the square root of 3638. I was pretty happy with that value because I knew it would go faster in the lower orbit. And so that made sense to me. The last question is, if we want to just go back and look at it. So I wanted to look at an escape velocity problem where you're not going from the surface of the planet, because I thought that this was important, so that we understand how to properly use that expression for escape velocity, or how we could find it on our own. We can find the expression for escape velocity by using the conservation of energy. We start off and say that assume that we're moving at the escape velocity. So that's our kinetic energy. And we look at the potential energy we have at our current location. So this is going to be the R final, which was 3.89 times 10 to the 6 meters. And then we say, if we truly move at the escape velocity, at the final situation, we have no kinetic energy, but we also have no potential energy because we've escaped from the gravitational pull of the planet. If we rearrange this equation, we can set these two terms equal to each other. And we can get rid of the mass of the satellite. It doesn't matter. We multiply by 2. We find the escape velocity squared could be given by 2g, the mass of Mars, over R final. And we take the square root to find our value. And when I did that, I found 4.68 times 10 to the third, which is 4.68 kilometers per second. Again, that made sense to me. I think this is right because the escape velocity from the surface of the planet is about 5 kilometers per second. It should be less when we're at an orbit because the gravitational pull that it's escaping from is a little bit weaker. So I hope that this is helpful to you because it's giving you a couple different types of things that you might have to do using the energy ideas for gravitation.